Welcome back to class today, and in our lesson today we are looking at the laws of logarithm. After we have looked at the laws of logarithm, in the subsequent videos we'll be looking at the simplifications involving logarithm. We look at substitutions in logarithm. We now look at equations involving logarithm, both simple linear equations, simultaneous equations, and equations involving quadratic. So we'll be looking at all of these things in the next 4 or 5 videos that will be dropping after this one. But in our lesson today, we are constraining our lesson to the laws of logarithm. And then what is the laws of logarithm? The laws of logarithm are those principles that guide the solution of logarithm. Anytime you have a logarithm problem to solve, there are principles, there are step-by-step methods you have to follow in order to arrive at a solution. That is what we consider as the laws of logarithm. So today, we'll be looking at about 12 of them. The first would be multiplication. I have logarithm of A, okay, I would use P. Logarithm of P times the logarithm of Q all to base P. Whenever you have two logarithms and whenever you have a logarithm and the terms of logarithm is multiplying or are multiplying, then you split them into addition of two logarithms. That is logarithm of P plus logarithm of Q, both in base B. So this is how we solve cases like this that involve multiplication. And vice versa, when you have addition, sometimes you are required to take it back to multiplication in order to simplify. Now let's look at an example. I have the logarithm of 35 to base 5. To simplify this, 35 is same as 5 times 7 to base 5. Then I can now split 5 and 7. So that would give us logarithm of 5 base 5 plus logarithm of 7 base 5. From there, we can simplify further. But for today, we are not solving the simplification. Subsequent videos will take us through the simplification of logarithm. Now, the second one I want us to consider is division law. If you have logarithm of P over logarithm of Q, all to base B, one of the laws of logarithm says you subtract the logarithm of these two terms. You subtract Q from P. Look at what I mean. We have logarithm of P minus the logarithm of Q all to base B. Just like we do a multiplication for here, instead of adding, we subtract. Okay. An example, I have the logarithm of 35 over 18, let's say to base 6. To simplify, we'll simply say logarithm of 35 base 6 minus logarithm of 18 to base 6. So this is how we handle division. And then sometimes you are given subtraction of two logarithms like this, and to simplify it may demand bringing it together as division like this. When we start solving simplification, you see us applying all of those rules. The third one we'll be looking at is logarithm of a number to its base. Let me use small letter b. Logarithm of a number to its base. Anytime you have a logarithm of a number to its base, it is always equal to 1. Look at an example. Log 10 base 10, the answer is 1. Log 2 to base 2, the answer is 1. So that is very basic and very simple. Now the next one we want to look at is logarithm of 1 is always 0 to any base. So if you have logarithm of 1, just know that it is what? 0. Log 1 to any base is equal to 0. Then E, the next one, power of a log number to base B. Anytime your log number or your log term has a power, take the power to the front of the logarithm. So we'll have n logarithm of P to base B. Let's see an example. I have logarithm of 3 to power 4 base 3. This 4 has to come to the front. Then it becomes 4 logarithm of 3 base 3. That's very simple. So the power will always come to the front. Then some cases, your base is what has the power and not your log term. Look at it. That is F. I have logarithm of p base b raised to power n. Your base has a power. What do? This power will come to the front as a reciprocal, right? A reciprocal means if I have 3, the reciprocal of 3 is 1 over 3. Reason is because 3 has a denominator 1. Every natural number has a denominator, invincible denominator of 1, as well as power of 1. But we're not talking about power now. So to take a reciprocal of a number means flip it. Denominator becomes numerator. Numerator becomes denominator. So if you have 6 over 7, its reciprocal is 7 over 6. All right. So applying that here, the reciprocal of n should be 1 over n. So to the front, I will write 1 over n logarithm of p base b. So this power has come to the front as a reciprocal. Look at this example. Logarithm of 4 to base 2 raised to power 3. 3 can come to the front and become 1 over 3 logarithm of 4 to base 2. So this guy, this power here came to the front as its reciprocal. What if I have logarithm of 8 to base 4 raised to power 2 over 5? The power is 2 over 5, the power to the base. Simplify it by writing the reciprocal of this power to the front of the logarithm. That becomes 5 over 2 logarithm of 8 base 4. So in all cases, anytime your base has a power, bring the power to the front of the logarithm as a reciprocal. When we start solving simplification of logarithm, you will see how we apply all of these things to solutions of logarithm. Don't miss the next video that we'll be dropping. Let's look at the next law, the inverse of the log term. I have logarithm of 1 over x base b. The same thing that happens when we are solving indices happens here. This can be written as logarithm of x raised to power minus 1 base b. And this power minus 1 is same as every power. So what happens to the power of a logarithm term? The power comes to the front of the logarithm. So that becomes what? Minus 1 logarithm of x base b. Let's look at this example. I have logarithm of 8 raised to power minus 1 base 2. Or I will write it as 1 over 8. So the next thing I want to do is to write this as logarithm of 8 inverse to base 2. Then this power comes to the front. I will then have minus logarithm. Of course, minus 1 cannot be, I cannot write 1 because 1 is a unitary, it's units. So I cannot come and write 1 logarithm. So I'll simply say minus logarithm 8 base 2. All right. So that and more will explain this principle or this law. Now H. So the next law we want to consider is if you have logarithm of p to base b to be equal to 1, the implication is that p is equal to b. Anytime you have a logarithm of a number to a certain base equal to 1, then you can equate the log term and the base. An example to that, I have logarithm of x base 4 equals 1. Anytime you have a logarithm of any number or any term to base a certain base equal to 1, simply equate x to 4. That's all. The next one we want to consider is the roots of logarithm number. I have logarithm of nth root of p, nth root of p to base b. So you know how we solve the nth root of any number in indices. It is not different. Another way we can write this is logarithm of p raised to power 1 over n. 1 over n, the nth root. If you have x, square root of x, how do we simplify it? It is something as x raised to power 1 over 2. But if this root has any number here, say 3, that becomes x raised to power 1 over 3. All right. So what if here is m? It becomes 1 over m. So this n represents any possible number. So when you have nth roots, any particular number to a particular term of a logarithm, simply write it as a fraction, whereas here becomes the denominator of that fraction. Then the power law will say apply. The power will come to the front, so that we now have 1 over n logarithm of p to base b. The power law has taken its course. Let's look at an example to that. I have logarithm of fourth root of 8 to base 3. This would give me logarithm of fourth root, means 8 raised to the power 1 over 4 to base 3. Power comes to the front, and then we have 1 over 4 logarithm of 8 base 3. Now, in some cases, this guy will also have a power. Look at this. What if I have logarithm of nth root of p to the power of m? Very simple. The same thing we do. We say logarithm of p raised to the power of m becomes numerator, and n remains at the bottom as the denominator. All right. So look at the example. Logarithm of 8, no, let's say third root of 8 raised to the power of 4. Raised to the power of 4. All right. So I would simply say this is logarithm of 8 raised to the power of 4 over 3. The power here remains numerator, the root here becomes denominator. Let's look at another law. Let's consider the 11th law. I have logarithm of p to base q multiplying logarithm of q to base p. Anytime a log number to a base switches their position, this is q and p now, and you multiply, it will definitely give you 1. That is how it works. An example, logarithm of 8 to base 4 multiplying logarithm of 4 to base 8. The power and the term has interswitched. When you multiply the both, you are having 1. And now the last of it all for now would be change of base. I have logarithm of p to base q. I can write p and q as the logarithm terms dividing themselves, introducing a natural base. Look at what this means. This becomes log p base 10 over log q base 10. Q used to be a base, but this time around, q has become the log term, whereas we introduce a natural base, which is 10. Look at this example. I have logarithm of 8 to base 7. This can never simplify. There's no how we can simplify logarithm of 8 to base 7. So in order to solve it, I will introduce a change of base. So this becomes logarithm of 8 to base 10 over logarithm of 7 to base 10. With this, we can simplify the function. So these are the laws of logarithm we'll be considering in the solving of simplification of logarithms. So in my next video, we are going to be looking at simplification of logarithm. Do well to return for that interesting episode. This is your assignment. Give 5 examples, one for each of the first 5 laws stated above. So for the laws we practiced, the first 5 of them, give 1 example for the first, 1 example for the second, and like that for the first 5 laws. Thank you so much for coming to class. See you in the next episode. Bye.